Rovibrational analysis even more. Okay, we're gonna acknowledge that as we go up in vibrational excitation, we actually change the equilibrium bond length slightly. And if we change the equilibrium bond length slightly, that changes the rotational constant. So in our last analysis, and the one you're doing for your homework, is you have BE, that equilibrium rotational constant with the equilibrium bond length. Well, now we have B0 for the zero vibrational state and B1 for the first vibrational state, the V equals 1. And we're going to have an R0, the bond length for the ground vibrational state, and R1 for that first vibrational excited state. And it could go on and on. You know, you could have a V12, a B12 and an R12 and so on. As we have anharmonicity, these are going to have different values. If we have a harmonic oscillator, a true harmonic oscillator, all of these values would be the same because the bond length would be the same all the way up, no matter what the vibrational excitation. And so even though we do have a real system, an anharmonic system, the HCl molecule, it's a pretty strong bond, and we're pretty deep in that well, and so there's not a lot of difference in the bond lengths and the rotational constants, but it's measurable. It's very measurable, and we'll see how precise we are in those measurements today. Then we're going to get into, I didn't put it on the title slide, the temperature analysis. So analyzing what temperature the gas is using the vibrational intensities. And then we'll use combination and difference analysis to get the B1 and the B0, the R1, R0, and centrifugal distortion for each of those levels. And then we'll finish up with this thing called nuclear spin statistics. And this is kind of bizarre. So you're doing rotational vibrational spectroscopy. You wouldn't expect the nucleus to get involved. Okay. But in symmetric molecules, when you have identical nuclei on either end, now that doesn't apply to HCl, but it does apply to CO2 or any of the homonuclear diatomics, your nuclear wave function comes in and messes with your intensities. And so it's really pretty cool to think about that we have a nuclear wave function that we never really do anything with. We do in NMR. We put these nuclei in magnetic fields, and we can detect the differences in nuclear spins, whether being with or against that magnetic field. So we can play with the nuclear spins, and in rotation, we can see those nuclear spins in very symmetric molecules. So those are the things we're going to talk about today. So here's some finer details that we can analyze in this Rovibrational analysis. With anharmonicity, we have different bond lengths in the upper and lower states, so we have different rotational constants, and we have slightly different vibrational frequencies. We have we can focus on these, and I'll explain how we pull the upper state data and the lower state data out of these spectra, and it's called combination difference analysis. I don't know where the word combination comes from, but that's just what it's been called traditionally. It's really difference analysis. So we're looking at specific differences in the lines, and these differences will give us upper state information or lower state information. And it will become clear to you what's going on when we look at the energy level diagram. We can also model the intensities to determine the rotational temperature. So we could look at a gas phase Rovibrational spectrum and model the temperature looking at those intensities. And then some of these rotational phenomena are modified by the nuclear wave function. So here's our difference analysis. So if we have the energy level diagram over there, and we look at the P1 line and the R1 line, that subscript tells us what energy level we're starting in. So if we take the difference between these two, that difference gives us information only about the upper state, because they start from the same position. So the lower state, there's no change in the lower state. But if we take differences between P1 and R1, or P2 and R2, or P3 and R3, we're getting information about the upper state only. So that's pretty cool. If you don't understand P and R branches, you can't understand this. So we had to do the other analysis, the 1.0 first. And then we're comfortable with the P1 and the R0 and the R1 and so on. So once we understand what those terms are, then we can start getting real picky, and we can say, let's find just the rotational constant and bond length in the upper vibrational state. And then let's figure out what kind of differences we can do to learn about the lower state. So these are differences that we will take. So here's, if we take the frequency of the R branch line and subtract the frequency of the P branch line that originate in the same J double prime, then we end up with these differences. The alpha E is really no different than the beta, the BE or term, and so we're just going to model the B term for this. There's a little bit of alpha thrown in there, so this B term could be more accurately modeled if we brought in the difference between B and alpha, but we're just going to stick with the B.
Which term is alpha?
The vibration rotation coupling constant. But because we don't see any difference we're only looking at the rotational differences in those upper levels, and so we're not really able to separate the tiny amount of the alpha interaction from this rotational constant interaction because of the differences that we're taking. Yeah, the differences end up being the same differences in J value. So really what we're modeling with this B1 has a pinch of alpha E in it.
Right.
I'll just say that. But it's like 10 to the minus 5 effect. And so it's really pretty small. Yeah, 10 to the minus 4, 10 to the minus 5. Okay, so here's our differences. So we take these frequencies, which we identified, the P and R branches. We did our peak picking. And so we have the R branch lines here, and we sort those according to J value. So this is R1, R2, R3, all the way down. And then this is P1, P2, P3, all the way down. Now we don't use the R0 because there's no corresponding P0. So we just start at R1. And then we take the differences in these frequencies. So I'm taking this R branch line, the 2925, and subtracting the 65, and I'm getting this difference of 60. So this difference is telling me some information about the upper state. In fact, it's telling me that it should be a difference of 4B as we go up. It starts out with an offset of 2, and then it goes up by 4B every time. And then we have this polynomial expression that gives us the dependence on that centrifugal distortion term. So we're going to have a J cubed term, a J squared term, and a J term over here. And you see those grow quite large quickly. So the benefit is we're getting information about the upper state. The downside is when you're taking difference analysis, your data is cut in half. Notice we have half the number of lines because we're taking differences. So whereas getting the full model of BE, we're using all of the lines to give us our equilibrium value, and we want to just know the upper state, we're going to only be able to use half the data because we're taking differences. And then we can use those, we can take different kinds of differences and get the lower state. So we did the regression analysis on these two columns here, B1 and D1, to kind of get that B value and centrifugal distortion value. So that was column 1 and column 2 for our regression. And we went ahead and modeled the intercept, even though there's no intercept in this equation. Just wanted to see what we would get. And sure enough, we got an intercept, and look at the p-value. 94% chance that value is caused by random noise. Perfect. Yeah, that's good. That's what we expect, right? There's no intercept in our model, and we modeled an intercept, and it says, it's not really there. Okay. And so that's a beautiful, example of the p-value, and also telling you that your model is pretty good too. This idea that we came up with. What?
Oh, look at the next p-value.
Oh, yeah, 10 to the minus 30.
Fine.
Yeah, 10 to the minus 15. Yeah, exactly. And I don't know if you remember from the lecture, Monday or whatever, but our B values were in the 10 range, and this is in the range of 10, and our D centrifugal distortion is a small number. So it's, 0.0005. And then, so we model it without an intercept, and so that intercept line has NA for all of its statistics and so on. It's set to 0, and our precision improved greatly. Okay, look at this. This 0.0005 here, so it's in the 4th decimal place, and this is in the 6th decimal place. So the uncertainty, this 3 goes right there. Okay, and then we modeled it again, and now the 5 is still there, but this this is now 1, 2, 3, 4, 5, 6. So yeah, so it was 3. Now it's dropped down to essentially 2, still in that same spot. So we cut our uncertainty in that D value by a third. So it's improved. Now we can take that B value and we can go through the reduced mass. Again, whenever you're doing reduced masses in your spreadsheets, use all of the, see here's it's not just 1 for hydrogen, it's 1.007825032. Okay, use your isotopic masses from NIST, chlorine 35, calculate your reduced mass, and then you can use that equation to get from B down to R. And so here's our bond length for HCl in the first vibrational level, so V equals 1 vibrational level. And it's a little bit longer than it was in the RE value that we determined the first analysis. And our uncertainty is down in the 5th decimal place. So that's pretty amazing. So that's the upper vibrational state analysis. Let's look at the lower vibrational state analysis. So how could we get differences in the lower state? We need these arrows to hit the same upper level. And remember, our subscripts are the lower level quantum numbers. And so if we go from 0 to 1, that's the R0 line. And if we go from 2 down here down to 1, then that's 1 in the upper state. So P2 starts down here at J double prime equals 2. So that's the P2 line. And delta J minus 1 for a P branch line. And so it comes up to 1. And then the R0 starts at 0 down here, and it's delta J plus 1. And so it's going from 0 to 1. So you see both of these hit the same level in the upper vibrational state, but they start at different levels in the ground state. So if we take the difference between P2 and R0, then we get only information about the V equals 0 rotational constant. Pretty clear? Okay, so then we set up the data. Here's our equation. And so everywhere we have in this difference for the R, let's see. Yeah, for the so this is the R0 line. Yeah, and so we're just setting up those J values here in our equation, and this is our difference. And so we make up our columns here, column 1 and column 2, and then we get the coefficients of those columns being B1 and D1. And so again, I just went ahead and modeled the intercept. Now this one is a little noisier apparently because it's showing that there might be an intercept effect. Okay, I'm going to go ahead and throw it out because my model doesn't have an intercept, but that last one was a beautiful example. This one's not so much. This is saying 0.01, so this is saying that's a real coefficient. But I'm going to throw it out and look at the other guys. So here's our rotational constant and its uncertainty and centrifugal distortion constant. Again, these are for the V equals 0 state. Pretty good R squared as well. And so here are our results from the combination difference analysis. Now, we have B0, 10.46, and B1, 10.13. You see it's getting smaller. It's getting smaller because the down here the bond length is short for B0 for R0, a little bit longer for R1. So as the bond length gets larger, the rotational constant gets smaller because they're inversely proportional by the square of R0 of R. And then here's our centrifugal distortion constant. Now we can use combination difference analysis. This is kind of a roundabout way to get to the equilibrium values, the E values. Notice I have BE, RE, and DE. If I have B1 and B0, I can get to BE by just assuming like a linear intercept. If I go from B1 and it gets smaller going to B, if I have, B1 and it gets bigger going to B0, what would it be at the equilibrium position of that potential well? I can just extrapolate down and get BE. So that's what we're doing here. We have the lower combination differences gave us these two values, the B0 and its uncertainty. The upper combination difference gave us the B1 values and its uncertainty. And I do this extrapolation. So here, the quantum state, V plus a half. So you can kind of think of this. Remember the potential well looks like this, right? And I have V equals 1, V equals 0. And this bottom part of the well is the E value. So when we talk about equilibrium value, we're saying the bond length at the bottom of that well, the rotational constant at the bottom of that well, the centrifugal distortion constant at the bottom of that well. And so we're taking this extrapolation, and I've just put it on its side here. Here's our B value. So this is B1, this is B0, and I'm extrapolating down in energy. See, this is quantum state, V plus a half. And I'm just extrapolating down to 0, which would be the BE value. Does that make sense, what I'm doing? I'm just finding that y-intercept. I go from 1.5 for B1 to 0.5 for B0. I'm going down to 0 where that hits, and that would be the BE value. So how do I do that? Well, it's a linear equation. I have 2 points, and so it's pretty easy to do. Y equals mx plus b. I can solve for m. So I take that again, and this would be the b1 is our y1 value, and b0 is our y0 value. And the difference between our quantum states there is 1.5 minus 0.5. So that's exact. There's no uncertainty there. And so then once I know my slope, I can solve for my b value, BE. So this is B0. This is our 0.5, which is right here. And I've got M, which goes right here. And so then B is the BE value. So I can solve for my intercept, which is BE, and that can give me that 10.63. So that's a sort of a roundabout way to get to BE. You know, we did it real easy with that first regression analysis where we used all 50 peaks or 20 peaks. But if you do combination of differences, you can still kind of get that BE value. But what about the uncertainty, right? Where does this uncertainty come from? Well, we've got this analysis down here. We could do our uncertainty. So this gets a little ugly, but I have the uncertainty in M, which is really just a difference. This X value, the difference in quantum number is just 1. It's exact. So it's just some difference. So my uncertainty in M is my uncertainty in each of my B values, right? That's this point 0027 and 00071. Those go right in here. And so I could get my uncertainty for my slope. I could get, with that uncertainty in slope, I could get my uncertainty in my B value. But I need to know the uncertainty in this product here. Okay, this MX value. So the MX is the multiplication. And so here we have, breaking this down, the m's actually cancel, and I end up with this uncertainty here, 0.5 times the uncertainty in the slope. And so there's my uncertainty in B. So this piece goes all the way up there, and that's where I get the point 0030. So you can get your uncertainty from all the other uncertainties that you have in this analysis. I did the same thing for R and the same thing for D. So that's where the RE came from and the DE came from. Now, how did we do? Well, we're really precise on these values. I mean, this is percent precision. Okay, so this value divided by that value times 100%, and it's 0.03%. That's my uncertainty in terms of my precision. And that's a 95% confidence value or coefficient of variation. We get down to DE, it's not so good because that's a harder term to determine. It really is that higher order term. 2% on D0 is 0.7% on D1, and that extrapolation gives us a 6.7%, 95% coefficient of variation. Well, I've got my E values from the CRC, so really these are the only ones that we should be looking at. Here, and here. You know, that's another reason why you want to calculate these RE values, because, you know, it's not fair to calculate my B0 to BE, right? Because they're two different things. One is the rotational state in the first vibrational excited state, and the other is the BE from the CRC. But we can take our experimental value minus the literature value, and that's what I mean by absolute bias. So we're 0.037 wave numbers high in our BE value from this determination, and only 0.003 wave numbers or angstroms low in our bond length. So we look at our accuracies. We got 99.7% of the literature value. But it's so strange. Our precision is so tight, okay, that it's not within, the literature value is not within our confidence intervals. So again, there's some bias in our spectrometer or something that's shifting us just ever so slightly off. We're less than 1% off, but we're so precise that we know that, you know, it's like some sort of calibration issue. It's not because we have sloppy data. The whole system's biased a slight amount. So I haven't determined what that is, so I need to go and figure out a way to, you know, tighten the calibration of the spectrometer in some way. Okay, let's combine this to the traditional analysis method. So we did the full analysis and got BE, AE, or alpha E, DE with the 1.0 analysis. And so we have, we can compare these values. So it looks like the traditional value performed better in this case. Let's look at BE compared to this one. So we were 99.96% accurate with our 1.0 analysis, just treating everything, all of the transitions, putting them all into a linear regression, pulling out alpha E, pulling out DE. That may be the strength of the traditional analysis, is that it's able to pull alpha E out of that BE value and increase its accuracy. Let's look at the bond lengths. Okay, here again, 99.98 for the traditional analysis. Combination and difference, just 99.8. So I think the traditional analysis works better. Again, I like the fact that we can pull that vibration rotation coupling constant out. Okay, let's shift gears a little bit to analyzing the temperature of this gas. So this is the intensity. It's related to the Boltzmann factor, the transition dipole moment integral, and then the line shape function. The line shape function doesn't change the intensity, it just smears it out. Okay. If we go through the analysis of that transition dipole moment integral, it gives a constant value. It sums to 1/2 actually, and so it's a constant for all the transitions. So the only thing that changes the intensity from peak to peak is the Boltzmann factor. Okay, so I just want that to sink in. Okay. And so the intensity of the rotational absorption depends only on the Boltzmann distribution, and that means the intensity is temperature dependent. So here's our Boltzmann distribution. Because in rotational systems, we have that degeneracy of 2J plus 1 out front. And then we have that E to the, that exponential dependence upon the energy divided by KT. So let's take the log of both sides so we can get rid of that exponent. And then again, we have a product here. So the log of the product is the sum of the logs. Okay, this log of E just brings down the exponent here. And now what I'm going to do is I'm going to switch sides with this. I'm going to bring this length of I, the intensity, over, and these will be the intensities of our transitions. And I'm going to bring the E over to the left side. And then I have a difference in logs, which is again the ratio. So I have the natural log of the 2J plus 1 over I. And then I brought that KT over to the other side. And so I have the energy equation as a function of the J values is equal to the temperature times Boltzmann's constant times the natural log of this ratio of the degeneracy over the intensities of our peaks. and that can be plotted. Okay, so I have the E sub j's plotted by K ln, this ratio, and the slope of that line is temperature. So I can just fit a line to that curve and get a temperature. Now, it seems like there's some offset. I'm not sure if this is related to the baselining of the data. I took the experimental spectrum, which had it had a non-zero baseline, and it was tilted slightly. So I did change the baseline of the data. I didn't shift it left or right, but this obviously is not a linear function. It's linear above j equals 1, or whatever this ratio is, 1. It's linear above here. It's pretty close to linear there. But it does have this problem down here at the bottom where it flattens out. And that throws our results off a little bit, okay? If we just put a line on here with no intercept, we get this 222.9 or 223 Kelvin, okay? And that gives us some, it's definitely got a good p-value, but you can see it doesn't really fit the data. So if we include an intercept, I don't exactly know what that intercept is. What is this? I mean, it's the units of Kelvin, but I've got a question mark on it. I don't know what that intercept represents, okay? But the slope is 351 Kelvin, okay? That's way hotter than room temperature. This is way colder than room temperature. This is, 273 is 0 Celsius. And so this is 50 degrees below zero. So that's kind of, but the point is, this is an analysis you can use to get rotational temperatures. That's also part of why it took me so long to do these notes. I had to check these results and make sure I couldn't find the problem, and so I beat my head on this a little bit. And so, it's one of those open questions. I wasn't able to answer it before today, and so trying to figure out what's going on. And also there's, you really need to have, if this model is going to hold well, your data needs to have, this zero intercept. And so our data has dropped some way. I don't know if it's because of baselining the data or what. But again, these are relative intensities, so it really shouldn't be impacted by just an offset like that.
Yeah, they'd all be opposite at the same time.
Yeah. So the slope wouldn't change. But anyway, kind of an interesting analysis nonetheless, even though our temperatures are off by, quite a bit, almost, 298, so 70 degrees from room temperature. Okay, so then we get into the nuclear spin statistics. So this is a new insight that quantum theory requires that the total wave function have certain symmetry properties, okay? And they're related to the different types of particles. So this is the first time we've really gotten into this idea of bosons versus fermions, okay? So for bosons, the total wave function must be symmetric under exchange of identical nuclei. So if you have a homonuclear diatomic, if you exchange the labels on those nuclei, then the total wave function should have a +1 character in front of it. So it should be symmetric under exchange, whereas for fermions, it should be asymmetric. There's one way to tell the difference between fermions and bosons, okay? Now, bosons have integer spins. Things like neutrons, the oxygen nucleus, things that have a +1 spin or +2 or 0 spin, like deuterium is a boson, okay? But fermions have half integer spins. Bosons don't obey the Pauli exclusion principle, but fermions do. So electrons, protons, the nucleus of a hydrogen, which is a proton, carbon-13. So different nuclei have different spins. They're classified, the nuclei are classified as bosons or fermions. And fermions do obey the Pauli exclusion principle. And so this total wave function is the multiplication of all the individual wave functions. We have translational wave function, rotation, vibration, electronic, and now nuclear. We haven't talked about the nuclear wave function at all up until this point. Okay. And so if the total wave function must be symmetric, then that puts requirements on all of the other wave functions. So let's dig into the individual wave functions. So symmetry analysis, the translational wave functions are not affected by exchange of nuclei. One other way to say that they're even. Vibrational wave functions are not affected by exchange. The only exception to that is maybe internal rotation. So if you have a methyl group and that methyl group rotates around, you're exchanging identical nuclei. And so you can see some nuclear spin statistics in the vibrational wave functions with the internal rotation. That's temperature dependent. So, at a low temperature, the methyl group may just oscillate like this. But at high temperature, it may spin. And so you may have different intensity ratios if you're at low temperature versus high temperature. And that's one way to determine the barrier to rotation for some of these things. You look at the spectrum and you warm it up, and when you see the intensity change, then you know that methyl is now freely spinning. So you think of toluene. That methyl is sort of locked in on toluene, but at a higher temperature, it'll spin freely. Then the electronic molecular orbitals. Okay, these would fit into the character table, just like the vibrational modes. And to determine the symmetry of the electronic MOs, we would find their Millikan notation, and we would look at these two pieces right here. So this sigma V times I. And so when sigma V times I is plus 1, then it's even under exchange. And so you see this 1 times 1 equals plus 1. So this is even. But this is a minus 1 times a plus 1. So that's minus 1. So this is odd. So this is a different kind of even and odd than Gerada and Ungerada. Okay? Gerada and Ungerada is just the I operator. In terms of nuclear spin statistics, it's sigma V times I. Okay. Now, why are we only focused on the D infinity H character table? Because we're only going to be dealing with diatomics that are symmetric. So not just homonuclear diatomics, but also linear molecules that are symmetric, like CO2, okay, which is also D infinity H. Now, what about C infinity V, other linear molecules? Well, those aren't symmetric, and so an HCl can't exchange equivalent nuclei because the nuclei are different on either end. So this is only for D infinity H type molecules, or maybe something like D3D, okay, but that would be a lot more difficult. So we're just going to focus on the linear ones. Now, again, when sigma V times I is equal to minus 1, then it's odd under exchange. And so we can see those examples down here. This one is going to be odd, and this one's going to be even. Okay. The doubly degenerate modes, the E's, they have one of each, and so it's going to open up on those. But we're really just going to focus on the A Millikan notations, the singly degenerate ones. And then when we get to the rotational motion, okay, the rotational motion, let me scratch out, this was a copy-paste error, so scratch that guy out right there. So we're just talking about rotational motion. They are the spherical harmonics. And the spherical harmonics for even quantum numbers are even under exchange, and for odd quantum numbers are odd under exchange. And this does sort of match that even-odd alternation of the rotational groups. They went from top row to whatever the rotation was, back to top row to whatever the rotation was. Okay. And then the nuclear spin statistics have different degeneracies, and this is where it really comes into play. So let's for even nuclear spin statistics, or when the wave function is even, then we call those ortho states, and we have this degeneracy. So this G was from the Boltzmann distribution. The degeneracy for the nuclear wave function has this, where I is the nuclear spin. So I is nuclear spin. Like for a carbon-13, a nuclear spin of 1/2. Okay. And then for the odd or para states, we call that para. the nuclear spin is, the statistics, the degeneracy is different. And this is the factor right here that changes the intensities in our system. So let's look at a couple of examples. Let's look at hydrogen. So our H nuclei are fermions. They have a half integer spin. Therefore, the total wave function must be asymmetric. So it should have a -1 character in front. Okay. So we do this in table format. Since the total wave function must be odd, let's just do this one row at a time. Okay. This total wave function must be odd. The translations are even. The rotation, let's say for even rotational levels is even. The vibrational is even. The electronic is even because it's an A1G in H2. That ground state has electrons in it that are in the A1G mode. And so therefore the nuclear state, since everything is even and the total wave function must be odd, then we must have our odd nuclear wave function here. That's a requirement. So if the J value is even, then the nuclear wave function must be odd. And it must have this degeneracy. So if I put a 1/2 in here, so 2 times a half is equal to 1, plus 1 is 2, so 2 times a half is equal to 1. So that's the degeneracy for the nuclear wave function. There's one way to put in these nuclei in the system when you have the odd nuclear wave function. Then the total wave function must be odd, and so when the rotational levels are odd, the nuclear wave function must be even. And this is the degeneracy for nuclear wave functions that are even. So you put in the 1/2 here, you end up with this being 2, and then you have a 1/2 plus 1, so that's 3 halves. 3 halves times 2 is equal to 3. Yeah, so we have 3 nuclear states that are even and 1 nuclear state that's odd. Okay, and it depends upon the rotational quantum number. This is really weird. This degeneracy now applies or is multiplied by those rotational degeneracies. So I have 3 times as many rotational levels that are odd than I do rotational levels that are even. And you say, how can that be? Really, can you not have that many rotational levels that are even? And the answer is yes. Look at the spectrum for hydrogen. Look at the intensity pattern. Do you see it? That's reflecting the number of rotational levels that are allowed by the nuclear wave function. So the nucleus is affecting the rotational wave function, and the rotational wave function symmetry is affecting the nuclear wave function. It's crazy. And so because we have, so this would be an odd rotational level. So this would be like, these are not P&R branches because they're not Rovibrational. This is pure rotation. And so we're just going to label these with J double prime. Okay. And so this is 0 going to 1. This is 1 going to 2. This is 2 going to 3. This is... You see that? And look at the odd ones. They have this degeneracy of 3. And so if you were to integrate those peaks, this would be 3 times this one. That's crazy, isn't it? This is not understandable without the acknowledgement of a nuclear wave function. I think that's pretty neat. You do a rotational spectrum and you see this alternation and you're like, what is that? Where does my intensity come from that gives this alternation? There's nothing in the rotational, translational, vibrational, or electronic wave functions that would give you that pattern. And so they had to dig deeper and they discovered the degeneracy of the nuclear wave function in this exchange requirement.
Is it applicable to the Stokes side?
Yes, it's also applicable to the Stokes side. Yeah. And so... and so then let's look at CO2, okay? CO2's oxygens have in oxygen 16 has a spin of 0. And it's because it's a spin of 0, it's a boson, and so therefore the wave function must be symmetric, okay, under exchange. And so let's do that analysis. The total wave function must be even. because it's a boson, okay? We'll just do this top row. My rotational levels are even here, so therefore everything's even, so therefore my nuclear wave function better be even. And so now I have the higher number of levels on this top row instead of the bottom row. I equals 0, so 2 times 0 is 0, plus 1 is 1. And then over here I have a 0 plus 1, so I have 1 times 1. Wait a second. Did I screw that up? Yeah, wait a second. Should be 1. Yeah, I can't do math. It was midnight almost. Okay, all right, minus 10. All right, so I got a 1 there. Let me just do this. I'm gonna draw a big 1. Everybody good with that? I'll put the little feet on there. Okay. Big, yeah, that's right. It's a 1. And so and then let's look at this bottom one here. So we do this. Now the rotational levels are odd. So I need something odd to cancel that out. So my nuclear wave function must be odd. Okay. And so I put in 0 here. I get 1. But then I put 0 here. I get 0. That's so it's a degeneracy of 0. Remember the Boltzmann factor has that G out front, e to the minus e over kt. If this is 0, then no level or peak. That's a bold claim. It's saying that I have a degeneracy of 0, so I can't have that energy level. That's so strange. Like a molecule can't have an odd rotational level if it's d infinity h with bosons on the end. Let's see if we can see this in the spectrum. So here's our CO2 spectrum. Okay, we've got all the P and R branches. You see those lines? It's pretty busy. So I'm going to take these two lines, just R0 and R1, okay? So these two lines here, because I know if I pick any two lines and I take the difference, it should be 2B. This is infrared, not Raman, okay? So infrared, the difference is 2B. Remember Hamlet, okay? So I take that difference and I say, now if that spacing is 2B, then B equals 0.75. But literature says B is 0.39. So it's a problem here, okay? Yeah, that's right. So let's take those and relabel those. What if those are not R0 and R1, but R1 and R3? Let's see. Yeah, and we'll let me work on this for a second. But R1, it should be like 0 and 2. And I take those differences, and if that's 4B, because I'm jumping by 2 different levels, then I divide that by 4, I get 0.38. And our literature value is 0.39. So it's saying I'm missing half of the row vibrational lines. So it's experimental evidence that those bosons of oxygen have eliminated half the rotational lines of CO2.
Yeah.
Yeah, they're not there. Those rotational lines don't exist. Yeah.
Imagine how busy it would be if it didn't
Right.
exist.
This is interesting too. This CO2 would be twice the global warmer that it is without the nuclear wave function. Isn't that crazy? It would absorb twice as much infrared light, which would make it twice the global warmer that it is. Yeah. So these are one of those little coincidences in nature that we're like, yeah, pretty crazy. So here's some other stuff. Now that we have those values, we get pretty good numbers for CO2. If we acknowledge the spin statistics, then we get really great numbers. If we didn't, if we were doing this right here, then we would be off on our wave function by 40%. On our not wave function, our bond length by 40%. Yeah. So it's pretty cool stuff, I think. Symmetry and spectroscopy, right? That's what this course is about. And this is exactly like the deepest dive into symmetry and spectroscopy that we'll go into. Okay. So this nuclear spin statistics.
Is there any reason why vibrational constant are affected by nuclear speed?
By the original what?
Rotational constant, they are affected by the nuclear wave function. Is there any reason why? I mean, why they are affected by nuclear wave function?
The original,
The rotational constant or rotational phenomenon. Why they are affected by the nuclear wave function?
I'm not sure. It's just the symmetry requirements. Is that what you're asking? Why? Yeah, it's the symmetry requirements of the wave function, which again, this is validation that those laws are valid, right? So we have these laws based on the symmetry of the bosons and fermions, and this is validation that those rules hold. Yeah, it doesn't affect the HCl because HCl is not a homonuclear diatomic. It's not symmetric enough to have this nuclear spin statistic requirement. It still has nuclear spin statistics, but there are no requirements on it. It's not this even odd exclusion thing. It's kind of like Raman and IR are now mutually exclusive. If you have a D infinity H or a inversion center, certain symmetry requirements pop up the more symmetric the molecule, and these spin statistics become really limiting when you have a symmetric molecule like CO2.
It's not illegal for everyone.
No, only when you have identical nuclei that can be exchanged. All right, cool.